Right. So this lesson is on simple machines, and to illustrate, right, imagine the problem of trying to lift up an elephant, right? Now, I'm just going to use an arbitrary number. I'm going to say, 10,000 newtons, right? And let's say 1 meter, right? This is the work that has to be done, okay? Now, wouldn't it be nice, we know to do this work on this elephant, right? We would have to do work on the elephant. This is the work that would be done, right? And this is the work we have to provide. But force times distance, right, which is what this is, times distance, right? Imagine if I could divvy it up such that I still got the same amount of work, but I had to apply less force. What would I have to change? I want force times distance to still be equal to 10,000 joules, okay?
Okay.
It's 10,000 joules. What would I have to do on the left side to still get 10,000 joules, but I want to use a smaller force?
Change distance.
Let's say I wanted to do, yes, exactly, 1,000 newtons, right? What would I have to do in order to get the same amount of work out? Multiply 1,000 newtons, not times 1 meter, but by 10 meters, right?
Yeah.
This would give me the same amount of work, right?
Yes.
And this is exactly what simple machines allow you to do, okay?
Okay.
People often say that, simple machines like pulleys or jacks or levers make the work easier, but that's simply not true. It's exactly the same amount of work you have to do. If you have to lift an elephant a meter, you have to do that amount of work, right? The weight of the elephant times 1 meter. You're going to have to put that work in, okay?
Okay.
The savings comes in the force that you have to apply, right, will be less in a good machine, okay?
All right.
We define machines based on their mechanical advantage, right? And that mechanical advantage tells me, well, if I want to lift a 10,000 Newton elephant, right, and I'm going to do it with 1,000 Newton force, right, my mechanical advantage is 10, okay?
Okay.
So let's look at that now. And the first machine I think we'll look at is a simple lever arm. I'm just going to draw an illustration of this. I'm going to call it D out, distance output, okay? And we'll call this distance L naught, and we'll call this distance L1. This was supposed to be L out, this will be L in. So in means the work, the force that you're applying, and out means the force that's coming out. Okay, so this is the input distance, and this is the output distance of the lever. This balance point here is called the fulcrum, and this distance here we will call D in. And so the mechanical advantage, which we'll just write as MA for mechanical advantage, is equal to D in divided by D out, which is also equal to, or proportional to rather, L in versus L out. Okay? So if the lever arm is 10, if Li is 10 and L out is 1, the mechanical advantage is 10. Okay? So this means that you can multiply your force, whatever force you apply on this end, on the input end, you will get 10 times the force on the output end, if the mechanical advantage is 10. Okay? Right. Realistically, this looks more like a 4 to 1, maybe a 5 to 1 ratio, if I were to measure this carefully, right? So in that case, we'd say if this was equal to 5, and this was equal to 1, then this would be equal to 5 over 1. That would be a mechanical advantage of 5.
All right.
Just wanted to match up with the picture a little bit. This also means, let me just note here, that the mechanical advantage is also equal to F out over F in. Okay? I should have put MA equals. Okay? So with this 5 to 1 mechanical advantage, right, that's what this tells me. So if this is 5, right, this is F out, then I can multiply both sides by F in. That tells me that the force on the output side is 5 times the force on the input side. I think Archimedes had made this statement, let me see if I can remember it, something like, I can move the earth if you give me the right lever.
Okay.
And a place to stand. Okay. All right, the next system I want to describe are pulleys, or sometimes called block and tackle, but we'll just call them pulleys. Okay, so I've got the illustrations drawn up here for 4 simple pulley systems. Okay, so these rods that you see here are connecting these 2 pulleys to each other. Okay, and the same thing here. There's no rod connecting this set of pulleys to this set of pulleys in any of these pictures. Okay, the red, those are the lines of the ropes that we would throw over it. Okay, so the whole basis of these pulley systems, if you remember, we did this example or a homework problem, I think. We had a picture hanging on the wall, right, and you had 2 pieces of line, right, holding it up, right, and the wider the angle was, you found that, as you increase that angle, right, the tension increased dramatically because you were doing mostly you're pulling to the side, and very little of the force components, the vector components of the force, are supporting the weight of the picture, right? But if I bring them together, right, so that the angle between them is 0 essentially, then I've divided the tension between the 2 lines, right?
Yeah.
And so that's what's happening with these pulley systems. You divide the tension between the number of lines that's supporting the weight, okay?
All right.
So if we look at the first one, right, how many lines are supporting the weight? The weight is this mass M here hanging, okay?
Okay.
Well, let's start with this line. Is this line supporting the weight?
Yes.
Yes, it is, right? Because the weight is pulling down on this line, there's a tension in that line holding it up, right?
Yeah.
So that's one line. What about this line here? This is the line where we're pulling, right? Is this line supporting the weight?
I thought that was the same line.
All the pulley is doing here is redirecting the direction of the force, right? So in this first case, right, and you can test it. Another way to think of it is, if I pull the rope 1 meter, let's say,
Yeah.
how far does the weight rise? Well, if I pull this rope 1 meter down, this weight is going to rise up 1 meter, right? Because it's just
Yes.
directly connected to the line. It's the same as if I were standing above pulling on the rope, right?
Yeah.
I pull it up 1 meter, the weight comes up 1 meter, right? It's the same thing here. The pulley is just redirecting the force, right, into a different direction. That's all it's doing. Okay? So there's only one line, in this case, supporting the weight of the object. And so the number of lines, that tells us what the mechanical advantage is. If we have 2 lines supporting the weight, we have a mechanical advantage of 2. Okay? So you can count the number of lines supporting the weight to give you the mechanical advantage. And so in this case, we only have 1, so our mechanical advantage is 1. So if we applied a force of, let's say, 100 newtons, right, in, we would get 100 newtons out. If we moved it 1 meter, then D out would also be 1 meter, right? The weight would rise up 1 meter, okay?
Okay.
Now let's contrast this with something that looks very similar, okay? Which is this picture here, okay? This one should remind you of the picture frame, right?
Yeah.
How many lines are supporting the weight now?
Let me see.
We've got this line, for sure, right?
Yeah.
But so is this line, right? If I let go of that rope, right, I would feel a downward pull, right?
Wait.
So we have 2 lines supporting the weight in this case, okay? So I'm dividing the tension between this and this, okay?
I'm confused now.
I know you have to think about it. Imagine if I were to pull up, right? If I pull up 1 meter, right,
Yeah.
what's happening?
It will come up 1 meter.
No.
Uh,
Think about it, right? The first 2 you're going to have to think about and get it straight in your head. You could even get a rope and try something like this, pull it up and see what happens, right? If I pull the rope 1 meter, right, what's going to happen? This is going to get closer. This will move up, but I think you just have to convince yourself, right? It's only going to come up half a meter, okay? So,
why?
well, again, you're just going to have to think about it, right? You have to get it straight in your head. It's a bit of a geometry problem, okay?
And in the first one, if we let go of that rope, the whole thing will fall down.
That's true, but it would also if I was just standing up on on an upper surface, holding the rope and having the weight dangle from it. If I let go, of course, it's going to fall down. The point is that this line and this line, they both are the same line essentially, okay?
Yes.
Yeah, this one you'll just have to think about. But if you think about it carefully, you'll see it and you'll get it, okay?
Okay.
But because there are 2 lines supporting the tension, this is again like the picture frame, right?
Yeah.
We've got 2 lines supporting the weight. The tension in the lines is half, right? You add up the tension in both lines, that's equal to the weight, right?
Okay.
So we've divided the weight in half. So another way of saying that is we have a mechanical advantage of 2, which which means that if we put in 100 newtons, right, we will get out 200 newtons, right? If we move it 1 meter, right, D out will be how far? Unfortunately, I erased my equations that I had up before, but you would have seen that the mechanical advantage, I'll write it up here, MA was equal to D in over D out, but it was also equal to force out divided by force in, okay? So if you solve for D out here, right, D out is equal to the D in, the distance you move it, right, divided by the mechanical advantage. So if we move it 1 meter, right, D out is only half a meter, okay? All right, let's look at the third system. How many lines do we have supporting the weight this time? Well, you can kind of cut across them and see, right? You got 1, 2, 3, 4 lines, right?
Yes.
So the tension is cut by 4 because there are 4 lines supporting it, okay?
Okay.
So that makes the mechanical advantage here 4, which means that if I put in 100 newtons, I will get out 400 newtons, okay? If I move it 1 meter, right, it will only move the weight 1/4 of a meter, okay?
Okay.
Remember, force times distance is work, right? So 100 times 1 is equal to 400 times 1/4, right? The work that I put in is the work I'm going to get out, right? You don't get free work, right? No perpetual motion. Remember that from the last lecture, right? Okay?
Okay.
And the final one, the final picture we have here, right? If we count the lines supporting the tension, we go across, say, this way. We see 1 line, 2 lines, 3 lines, 4 lines, 5 lines. That means we have a mechanical advantage of 5. Which means that if we put in 100 newtons, we will get out 500 newtons. And if I move it 1 meter, it will move the weight 1/5 of a meter. Okay?
Okay.
So it's really what you're trading off, right, is you have to move a lot farther, right, but with a much lighter force, or a much lower force, in order to move the heavy weight a shorter distance. Okay?
Okay.
Okay, the next one I want to illustrate are inclined planes. And so we'll call this section of it, how to build the pyramids. Okay? So now we're going to look at our favorite inclined plane. Okay, and we're going to imagine pushing this block up this inclined plane. Okay? Now, I've labeled, right, the D in, right, so we're going to think of this as a machine now, okay? So the distance in versus the distance out, right? In order to get this block up, I used, the 3, 4, 5 triangle because that's a happy triangle, right? It's a nice 90-degree triangle. It's actually a triangle the Egyptians knew well, right? They would tie these knots and ropes, right? So that they could get the 3, the 4, and the 5, and then they could use that to determine a 90-degree angle. Just by putting your foot on one knot, holding the other one, and having someone put their foot down on the other one, bring it together, right? You can get a 90-degree angle quite nicely. So they knew the 3, 4, 5 triangle, okay? So here's the weight, right? We're going to push up the hill, right? The work that we're doing, right, if you recall, is the work against gravity, taking it from 0 meters up to, say, 3 meters, okay?
Okay.
Or from 0 to 30 meters, whatever you want, right? If you're building a pyramid, it's probably more like 30 meters, not 3 meters. So I've tried to label the different parts, and if you think about it, it should make sense to you. Of course, you have the weight of gravity pulling straight down. You're applying a force, right, in the direction of this incline, right? So the Fn is this right here, okay?
Okay.
Now, let me ask you this. Who can tell me what the mechanical advantage of this machine is if we built our incline based on the 3, 4, 5 triangle?
That'd be 5 over 3.
Yeah, very good, right? The mechanical advantage here, right, is D in over D out, which in this case, D in is 5 or 50, whatever, right?
Yeah.
5 over D out is 3, right? So our mechanical advantage here is 5/3.
Okay.
Okay? It's not as good as, the mechanical advantage of 5 that we had before with the pulleys, but it'll do. Okay? And so if you think about the pyramids when they were being built, I think I have some numbers here. Let's see. If you imagine that this is the top of the pyramid, right? When they built these things, they constructed these ramps that went up the pyramid. You could make the ramps out of earth. You would, underneath each of the blocks, you'd put logs so that they would roll. So it was more of a, try to lower the friction, right, that you experience as you pushed it. And with a 3, 4, 5 triangle, which they knew, and it's not that, horrible of an angle, right? So D out, or excuse me, F out, right, needs to be 25,000 newtons for like the average stone in the pyramid. And so you could divide that by the mechanical advantage, right, to figure out what the Fn needs to be, right? So if you divide that by 5/3, the same thing as multiplying by 3/5 times 25,000 newtons, and that would give us, that's 15,000 newtons, right? 15,000 newtons that we have to push. The average worker, right, so F of man, if you will, is about 300 newtons. I forget where I found that information. I can't testify to the accuracy of it. And so if you took this 15,000 newtons, right, and you divided it by the force that one man can provide, right, 300 newtons, you would come up with something on the order of 50 men. And that's a reasonable number, right? You don't need a slave army to push these, 2,000-ton stones up the pyramid to construct it. And you certainly don't need spaceships to levitate them and put them in place. It's quite doable, even with a small workforce, especially by ancient standards, right, where workforces tended to be pretty large. Okay? So pyramids were definitely doable just using simple machines like an inclined plane, even for the heaviest of stones, which would require maybe twice as many men, but it wouldn't be ridiculous. I think the largest stone that they find in the pyramids was would have required 80,000 newtons, and that would require about 160 men to push. They had oxen too, so pretty sure. I'm not certain of that if they had oxen or not, but they may have. They came from that region, so yeah. So that's a simple machine that you can use to build some pyramids. Okay.
Okay.
The last thing I was going to mention, right? There's another way to look at this, right? At this inclined plane machine, right? If you could think of it like this. So I'll draw that. Just flip the direction of it. This is still the 3. This is still the 4. This is still the 5, right? If I have a weight of, let's say, 1 pound, right? 1 pound, right? And a pulley here, right? Which is just simply redirecting this, right? What is the weight that I need to drag this up the hill, right? It's not 1 pound, right? I'll give you a hint, right?
2 pounds?
No, it's not 2. It's not 2 pounds, right? It's, I'll make it a little bit bigger. It's 3/5 of a pound, right? 3/5 of a pound. Now there was this famous. It's called the epitaph of Stevinus, right? It's one of these. You draw a picture and you say, "Behold." And if you are smart enough to think about it, then you'll be like, "Oh, yeah, I get it. I see it." There was a nice proof of the Pythagorean theorem that simply drew a picture and said, "Behold." I thought it was a great proof. But, so Stevinus did something like this. He drew these balls of equal mass. There should be 3 of them on this one. We'll kind of ignore the loop around here. We need 2, 3, 4, 5. And these are all connected, with a line. And the mass of each of these balls is the same. Right, and then, of course, we have some balls hanging below it. I don't think the number matters, but they're equally spaced, right? And the masses of each of these balls are the same, right? And so what this, you can read this any way you want. You can think, well, this means there's no perpetual motion, right? This thing is not going to, I could set it into motion. If it was frictionless, it would continue to rotate around this 3, 4, 5 triangle, right? You can glean that this is a 3, 4, 5 triangle just by assuming these are equally spaced balls. You see 3 of them on this side, 5 of them on that side, right? But this is saying, right, that it takes, only 3 masses to pull up 5 masses up this inclined plane, okay?
Okay.
It also, in a way, says there's no perpetual motion, right? So if it's left in a state of rest, it's not going to start moving on its own, okay?
Okay.
But that's something to think about. You can look that up on the internet. It'd be a fun research topic, the epitaph of Stevinus. And that's all I have to say about simple machines.